Okay, we're working on a Robocop today. It's a Dataeast, kind of an early game. Seemingly works, but it has two problems with, I think it's this slingshot and that pop bumper. What happens is they're locked on. Well, they're obviously not locked on now because the guy I got it from wanted to play the game, so what he did is he just cut the ground returns off the coil. Like right here you can see. This is the slingshot coil, this is the power, the red wires, this is the ground return, and look, if I touch it just momentarily, like that, it doesn't fire. But if I start a game and touch it, it does. Now let's go down to the pop bumper, same thing, down in this pop bumper. Again, he's got the power wires there, but this wire here is the ground return, and I touch it, nothing. But let me put the balls in it and start a game, and I'll show you how they're locked on. Okay, so I have the game in game mode. You can see it's waiting for me to do something. And I'll take this ground wire now on the slingshot and put it on there, and see how it locks on? As soon as I let it off, it lets up. Likewise, down on this coil, same thing, the pop bumper. So, let's talk about this. The interesting thing is these are special solenoids, so they can be controlled either by the CPU or by like physical mechanical switches. So there could be a problem up here on the slingshot. You see how there's a capacitor on here and a resistor. Sometimes the capacitor is short, making the switch, the mechanical switch, which is not part of the switch matrix, keep the coil on. Same thing could have happened down here. He's got a little capacitor right there, and we could check that. So just to be clear on this, what happens with these games is there's two sets of switches. There's the mechanical switch up here, which actually fires the coil, but it's not part of the switch matrix. And then as the coil fires, you can see this switch right here that closes, that actually is part of the switch matrix and scores the point. This is how Williams and Dataeast did their special solenoids. They did it to get quicker action because the CPU is actually not involved in the firing of the coils. It is purely a mechanical switch going back to the driver board that physically fires the coil without any CPU interpretation. So the interesting thing on this is that the coils do not fire when you turn the game on. Okay, it only happens after the game is started. That implies that there is a switch input problem in the circuit, not necessarily a driver transistor problem. So usually, like over here, this is the special solenoid section of the board, and these are there's 6 special solenoids, and these are the 6 driver transistors for them, and there's 6 pre-drivers. Normally one of these guys shorts and the coil locks on. But if one of these was shorted, the coil would lock on right when I first turn the game on, not just when I start a game. So that means that we have switch input problem up here. So to check these inputs, the first thing I want to do is lift the playfield and see what wire colors, or you can use the schematics, control these kickers. So on this slingshot kicker, right here is the input wire, and this is orange with the yellow stripe. Okay, then if we go down to the pop bumper, the input wire is this orange wire right here, and this is just straight orange with no stripes. Okay, so that's real important to remember, because what we're going to do is we're going to go to the back box and check this input connector. So now what you'll see is that there's 5 orange wires. Now why are there 5 orange wires? Because we've got 5 devices, 5 special solenoids we're controlling. 1, 2, 3, 4, 5. So that means you got 5 input wires, and then this one white wire is a common wire. So we're going to ignore that one. But we want to look at these. And what we're going to do is we're going to use a logic probe, and these switch inputs should all be high, okay? Because what happens is when the skirt is hit here, what it does is it makes that input go low, and that's what tells this circuit to fire that coil through these transistors. Now my handy meter has a logic probe built into it, so I got my black wire on ground, and obviously it's turned on. And what I'm going to do is I'm going to go up here and I'm going to look at the first wire, the very topmost orange wire. And you can see my signal is high. You see that little arrow that appears right here? That tells me that my signal is high, okay? Now I'm gonna go down one more, and again, my signal is high. See, there, I'll unprobe it and then probe it, and you see it's high. Now we're gonna go third one down, which is the orange and yellow wire, which is our stuck-on slingshot. So now look, my logic probe now shows that that's low. So that means that is being forced low, and that's why that slingshot is locked on. Because remember, these are not one-shot coils. These are not computer controlled, which means if a ball gets stuck on a slingshot or a pop bumper in this era, System 11 or Dataeast, the coil will stay energized. And that's exactly why these things are locked on during game mode. So now let's go down one more, and again, it's a low signal, and that is the orange wire, so that's our stuck-on pop bumper. And then the last one is this one here, and you can see that's high, what we'd want to expect. So out of the 5 input signals, 2 of them are stuck low. Now the question is this a playfield problem, or is it a problem on the board? So that's easy to diagnose. We can just pull this connector off, like that, and then we can check it again. Let's see, it's third one down, or actually fourth one, because the first one's a key, then 1, 2, 3, so, and look, it's still low. So now that one is the orange with the yellow wire, and the one right below it is the regular orange, and they are both still low, opposed to the ones that are high, like the topmost one, signifying that the problem is indeed on the board, because we could have had a playfield switch error, but removing this connector tells us the problem's on the board. So let's pull the board and take it to the bench. Before we start going nuts, let's check the schematics. Remember, as I was telling you, this is the upper right portion of the driver board. That is the section right here. And you can see, just like I told you before, special coil switch inputs. These 2 chips and this connector. And then here is the special coil drives. These are the transistors that usually short. But we know it's probably not this. We believe it to be the switch input problem. So it could basically be either of these 2 chips, and we can check the schematics to figure that out. But I should warn you, before we get any further, there is a slight caveat in this design. If you look closely here, in this area, this is our connector, and remember it was the 4th pin down, so the first one's key, 1, 2, 3. It goes off to these 8 capacitors and diodes. And what these little diodes are, there's Xenier diodes, and they are rated at like 8 volts, and if anything goes over 8 volts, that is somebody shorts coil voltage or a flash lamp to the switch inputs, it'll blow these guys up before, in theory, it gets to the chip and ultimately the, possibly the PIAs or even anything backwards. So we need to check these little guys first before we start going nuts with the chips, because taking the chips out is a lot more work. Well, this one's socketed, so that one's no work, but it's a lot more work than taking these guys out. This is only 2 solder points, and this is 14 for each of these chips. So let's check those diodes first. I got my meter set to diode function, and then I'm going to take my black lead and put it on the banded side of each diode, and the red lead on the other. And I should get between 0.4 and 0.6, like right here. That initial beep on this fluke means that I'm in good range. I have 0.670. Next one down, this would be the second wire down. Same thing, 0.6. But if I go to the 4th one, or the 3rd one down, which is our 4th pin down, which is our slingshot kicker, it is shorted, 0.02. And if we go to the next one down, which is our pop bumper, it's also shorted. That's even 0.000. Next to last one down, 0.6 and 0.6. So check that out. 0.6, 0.6, shorted, 0.6, 0.6. So the problem actually isn't either one of these chips. It's one of these little Xenier diodes that are right here, and they correspond. You see I have the pins marked in blue right there. So the 1, 2, 3rd, and 4th pin down with the little blue lines corresponds to the 1, 2, 3rd, and 4th diode down that are shorted. I replace those diodes, I can guarantee you that those kickers are now going to work. I have the 2 new diodes put in. Now the original 1N5234s, which are 6.1 volt, 6.2 volt Xenier diodes. I put in the slightly larger 1N4735s, which are, you can see they're physically a little bigger because they're an increased wattage. I think that goes from quarter watt to half watt. It doesn't matter, they're just easier to get, the 1N4735s. The important part is the 6.2 volts. Anyways, if we trace this guy here goes up to this guy, pin 2, and this guy here goes over to this one, pin 8. So it goes to this chip. So I figured since the thing's socketed, I might as well test it. Here's this nifty little chip tester. Even though I have a chip in here, this is actually the original one. We'll just test it. 7402, and that's what the chip is. It is a TTL chip, a 7402, and we can see that it actually tests good. So the problem was not the chips, it was indeed the Xenier diodes. So now I will put this back in the game. Now I've got it in Diagnostics, and as soon as you do that, the flippers become active, as do the special solenoids. So as you notice, not locked on, not locked on. Look, now it's working. Likewise, pop bumpers, they're all working too. So we have fixed our problem with the change of the Xenier diode up here in the special solenoid switch input section. It was not, in fact, the chip, but one of these Xenier diodes.